Good evening all. Today we are going to see about error control coding in digital communication. Channel coding theorem states that it is possible to transmit information with an arbitrarily small probability of error provided that information rate R is less than or equal to a rate C called channel capacity. It can be stated again that given a source of m equally likely messages with m greater than 1, it is generating information data rate R given channel with channel capacity C, R is less than or equal to C. There exists a coding technique such that the output of the source may be transmitted over the channel with a probability of error in the received message which may be made arbitrarily small. The block diagram of a digital communication system with channel coding is as shown here. First, the input message bits are fed to a channel encoder. Output of the channel encoder is fed to the modulator, from where it is fed to the discrete channel, and the noise is added there. This noisy signal from the channel is received by the demodulator, and then the demodulated signal is fed to the channel decoder, from which we will be able to retrieve the original message bits. Error control coding. The transmission of the data over the channel depends upon the two parameters, transmitted power and the channel bandwidth, the power spectral density of a channel noise, and these two parameters determine the signal to noise power ratio. That is, signal to noise power ratio is determined by power spectral density of the channel noise, transmitted power, and the channel bandwidth. The signal to noise power ratio determines the probability of error of the modulation scheme. For a given signal to noise ratio, the error probability can be reduced further by using coding techniques. The channel encoder adds extra bits, that is redundancy, to the message bits. Encoded signal is then transmitted over the noisy channel. The channel decoder identifies the redundant bits and uses them to detect and correct the errors in the message bits it saves. Thus, the channel encoder is used at the transmitter side, and the channel decoder is used at the receiver side. The channel encoder adds extra bits to the message bit, that is redundant bits. And then the channel decoder identifies the redundant bits and uses them to detect and correct errors in the message bits. Error control coding can be classified into two types. One is known as the block codes and another one is known as the convolutional code. These codes, that is the block codes, consist of n number of bits in one block or the code word. This code word consists of k message bits, and n minus k will be the redundant bits, or the check bits or the parity bits. Such type of codes are called as block codes, and is called as n, k block codes, where the n represents the total number of bits in one block or the code word, and k represents the messages in the code word. Convolutional codes. In convolutional codes, the coding operation is discrete time convolution of the input sequence with the impulse response of the encoder. The convolutional encoder accepts the message bits continuously and generates an encoded sequence continuously. Important terms used in error control coding are code word. The code word represents the encoded block of n bits. It contains the message bit and the redundant bits. Code rate, the ratio of message bits and the encoder output bits, is called the code rate. Code rate is defined by R and it is mathematically given as k by n. Hamming distance. The Hamming distance between the two code vectors is equal to the number of elements in which they differ. If you have the code as x is equal to 101 and y is equivalent to 110, then these two codes differ only in second and the third bits. Therefore, the Hamming distance between x and y is noted as 2. Minimum distance. Minimum distance is the Hamming distance between the valid code vectors. Code efficiency is the ratio of the message bits in a block to the transmitted bits for that block by the encoder. It can be stated mathematically as code efficiency is equal to K by N. Weight of the code. The number of non-zero elements in the transmitted code vector is called the vector weight. It is denoted by W of X, where X is a code vector. For example, if you have the code 0111101, then the weight of this code vector will be W of X is equal to 5, since it has 5 number of ones in the code vector. Linear block code. Principle is for a block of K message bits, N minus K parity bits or check bits are added. Hence, the total bits at the output of the channel encoder or N. Such codes are called N, K block codes. Next, we shall see about the Hamming code. Hamming code is one type of linear block code. These codes satisfy the following condition. Number of check bits Q must be greater than or equal to 3. Block length N must be equal to 2Q minus 1. And number of message bits K equal to N minus Q. Minimum distance must be equal to 3. So we have to note down that Hamming code is one type of linear block code which satisfies a special condition such that check bits are greater than or equal to 3 and the block length is 2Q minus 1 and the minimum distance must be equivalent to 3. Further, we can manipulate that R equal to K by N. Substituting K value is equal to N minus Q. You get the equation as N minus Q by N, which can be again rewritten as 1 minus Q by N. Putting the value of N is equal to 2 power Q minus 1, we get 1 minus Q by 2 power Q minus 1. Error detection and correction capabilities of the Hamming code. Since the minimum distance of the Hamming code is 3, it can be used to detect double errors or correct single errors. We shall see the distance requirement and the errors that can be corrected and detected by the Hamming code. So first point is to detect up to S errors per word. D minimum should satisfy the condition that it must be greater than or equal to S plus 1, where S represents the number of errors. Then the condition for correcting T errors is given by D minimum is greater than or equal to 2T plus 1. Then correcting up to 2 T errors and detect S greater than T errors is given by D minimum must be greater than or equal to T plus S plus 1. So by having the condition satisfied by the D minimum, the code will be able to detect errors or correct errors, or it will be able to detect and correct errors. So from that equation, you can note on that for detecting double errors, D minimum should be greater than or equal to 3. And for correcting one error, it should be greater than or equal to 3. For better understanding, we shall see one problem. The parity check matrix of a particular 7, 4 linear block code is given by H is equivalent to matrix as shown here. Find the generated matrix G, list all the code vectors, minimum distance between the code vectors, and how many errors can be detected, how many errors can be corrected. Now let us note down the value of the N and K, that is the number of total bits and number of the message bits. So since it is given that it is a 7, 4 block code, N is equivalent to 7 and K equal to 4. Therefore, check bits is N minus K equivalent to 7 minus 4 equal to Q is equal to 3 bits. So totally there will be 3 check bits. So to obtain the generated matrix, we have to note down that we have a check matrix represented by H is equivalent to P transpose IQ, where P represents a parity and then I represents an identity matrix. Here H is given like this. So from this H, we'll be able to note down the P matrix by transposing the first half of the matrix. So this 1110 becomes 1110 row wise becomes column wise. Similarly, the next column will be 1101 and then the last column will be 1011. Next, in order to calculate the generator matrix, you have to note down the identity matrix first and then note down the parity matrix. Since you have the condition that parity is of the order k cross q, definitely I should be of the order k. So you substitute this I with 4 cross 4 matrix, 4 cross 4 identity matrix, and then it should be noted with the parity matrix. So in this way, you'll be able to note down the generator matrix. Next, from the generator matrix, you'll be able to obtain the check bits. So check bit is given by the relation C is equivalent to M into P, where M represents a message bit, P represents a parity. So C1, C2, C3 can be mathematically noted as M1, M2, M3, M4 into P. So since P is a 4 cross 3 matrix, surely your M columns must be equivalent to 4. So you choose it as a 1 cross 4 matrix. Message is of 1 cross 4 matrix as shown here. So you substitute for the P matrix. Then by multiplying this message bits with the parity bits, we'll be able to note down the check bits. So for example, if you consider C1 means it will be equivalent to M1 multiplied by 1 plus M2 multiplied by 1 plus M3 multiplied by 1 plus M4 multiplied by 0. Here you have to replace your addition by modulo addition. So you have the condition of C1 equivalent to M1 XOR M2 XOR M3 and C2 equivalent to M1 XOR M2 XOR M4. C3 equal to M1 XOR M3 XOR M4. So on having these relations, we will be able to note down the code vector. So first is you have to form a table like this provided with a message vector, check bits, and then the code vector of the core word, and then the weight of the code vector. So in the message vector we have 4 bits. So you have to write all the 4 possible combinations. So you have the entries from 00 till 15 you have to enter here. So there are possible combinations is 1 to 16. And then you can calculate C1 from the relation that it will be equivalent to M1 XOR M2 XOR M3. So here the first is M1 XOR M2 XOR M3. So it will be equivalent to 0. So it is 0. And then here you have 0. So again it is 0. Here you have 1. So it is 1. Here you have 1. So again 1. And then this 1 is shifted here. So you get it as 1. So whenever you have odd number of ones in M1, M2, M3, you have the C1 as 1. Otherwise, it will be equivalent to 0. Similarly, you have to note down your C2 with respect to this equation M1, M2, M4. So between these, you have to perform the modulo addition, that is XOR operation. So from the table, you will be able to note down your M1, M2, and M4. So from this, you can find out your C2. So here M1, M2 is 0, 0, and then M4 is 1. So your C3 is 1. So if you have odd number of ones in M1, M2, M4, then you can note down your C2 is equivalent to 1. So in this way, you'll be able to fill the columns C2, and then C3 can be noted from this relation M1 XOR M3 XOR M4. And after that, you can write down the code word, which is the combination of the message vector and the check bits. Then after noting down the code word, you can note down the weight of the code vector. So here you have no 1, so 0. So here you have 3 1s, so 3. Here also you have 3, 4, 3 1s. So from this to this, M1 till C3. Similarly, here you have again 3 1s, and then you have 4 1s. So in this way, you have to note down the weight of the code word. So minimum weight here is nothing but equal to 3, non-zero minimum weight. So the smallest weight of any non-zero code vector is 3. D minimum is equal to 3. Error detection and correction capability. Since D minimum is equal to 3, you have to substitute in the equation d minimum greater than or equal to s plus 1, where s represents the errors that can be detected. 3 greater than or equal to s plus 1, so it will be equivalent to s will be rewriting the equation, you get s is less than or equal to 2. So it will be able to detect 2 errors. Then d minimum is greater than or equal to 2t plus 1. This is the relationship for correcting the errors. So 3 greater than or equal to 2t plus 1. So t is less than or equal to 1. So you'll be able to correct one error. And then this is the encoder of the Hamming code. Dependent upon the relation between your C3 and other, that is dependent relation between the message bits and the check bits, you'll be able to draw the encoder. So C3 is given by M1 XOR M3 XOR M4. Similarly, C2 is given by M1 XOR M2 XOR M4. And then similarly, C1 is equal to M1 XOR M3, M1 XOR M3. So in this way, you'll be able to note down the encoder of the Hamming code. So here you have a switch-like portion so that it will be traversing from message register to the check bit register, so that we'll be able to get the code words in sequence from both the registers. So dependent upon the input bit sequence, you'll be able to generate your code words. The next problem, for a systematic 6,3 linear block code and generator matrix are given, find all the code vectors, draw the encoder circuit for the above code, and then find the minimum Hamming weight. So here G is given by I3, P3 cross 3. So since it is a parity matrix from the picture, from the given data that is G, you will be note down that this is your P matrix given by this. So P matrix is given by 1 0 1, 0 1 1, and then 1 1 0. And then the check bit is given by the relation C equal to M into P. M represents a message bit and P represents a parity bit. So as this is 3 check bits are there, you have 3 messages and 3 cross 3 parity matrix. So from this multiplication, that is M1 into N plus M3. So from this matrix multiplication, you will be able to note down the equation for the check bit. C1 equivalent to M1 XOR M3, C2 equivalent to M2 XOR M3, C3 equivalent to M1 XOR M2. With this relation, you will be able to generate the code. So here you have the M1, M2, M3. So list all the possible combinations from 0 to 7. And then for calculating C1, you have to consider the relation as M1 XOR M3. So M1 XOR M3, 0 0, 0 1, so 1, 0 0 0, 0 1 1, 1 0 0. So it is 1. So in this way, you'll be able to note down the check bits. After noting down the check bit C1, you have to note down for C2 that's given by M2 XOR M3. So in this tabulation, you have the M2, M3. So XORing this M2 and M3, you get this C2 column. And then C3 is given by the relation M1 XOR M2. So first 2 columns represent your M1, M2. So XORing this, you will get 1 here. Similarly, here also 1, here 1. Again, it will be 0. So in this way, you have to note down the check bits. Then you have to write both the check bits and the message bits together. This represents the final code vector X. And then you note down the weight of the code W of X. So here this code consists of no 1, so it is 0. It has 3 ones and then 3 ones and then 4 ones. Again, finally you will be noting that this consists of 3 ones. So the weight of the code is equivalent to 3. So D minimum will be equivalent to 3 here. So from the relationship between the messages and the code vectors, you'll be able to draw the encoder circuit. and the switch traverses from messages to the check bit so that it will be able to provide a correct code. So thank you all. We shall see the rest of the things in the next class.